Hello, welcome everyone to the fourth talk of the third session of IWQC 2020. And the next speaker will be Richie Yeung, talking about a simplification method for layered quantum circuits of mixed phase gadgets. Richie, the floor is yours.
Thanks, Ross. Hi, everyone. Thanks for having me. Today, I'm going to talk about a method for simplifying circuits of mixed phase gadgets, which are a special case of poly gadgets. This talk is based on some of the work developed with Stefano Gogioso during my master's thesis at the University of Oxford. Now, I know Alex Kautan and others have already discussed phase gadgets and poly gadgets in an earlier talk today, but I'm going to talk about them again at a slower pace, particularly for those unfamiliar with ZX calculus. So in ZX calculus, we have ZX diagrams, and ZX diagrams are made of Z and X spiders. And Z and X spiders are pretty general. Here's their definition and Dirac notation. And effectively, you can build any quantum circuit using these spiders. Those familiar with ZX calculus would notice that my definition is slightly different. It doesn't matter, it's only to match the description of certain gates in QML ansätze. And the rules you know in ZX calculus apply still to these spiders. So using these spiders, we can construct commonly used quantum gates. In particular, we have the Z rotation gate with the X rotation gate, and we have the CNOT gate here. The CNOT gate actually doesn't have a phase on it. That is because the CNOT has phase 0, so we just omit it because we don't need to write it down. Here we also have the Z phase gadget and the X phase gadget, which are generalizations of the rotation gates. And what they do is effectively the phase gadget in the rotation gate, you rotate based on whether the input is 0 or 1. In the phase gadget, you rotate based on whether the phase gadget has a parity, odd parity, or even parity. Z and X phase gadgets can be written as poly-exponentials. So it is in this sense that they are specializations of poly gadgets. In poly gadgets, you're allowed to have the exponent be tensor products of Z gadgets, X gadgets, I gadgets, Y gadgets, Z polys, X, Y polys. But here you can only have Zi, either all of Zi or all of Xi. And in fact, the X phase gadget is just the Z phase gadget with Hadamard's on the left and on the right. So it's just a change of basis. So for those who are unfamiliar with ZX calculus, don't worry, because we're only working with a fragment of the ZX calculus, which only concerns these phase gadgets. And the rules that I describe here apply to the Z phase gadgets in green shown here, and also the red phase gadgets for the X basis. So the first two rules are the phase gadgets add when the legs of the phase gadgets match. So they add together when they fuse. And then another property is that these phase gadgets of the same color or the same basis commute with each other. So you can imagine the legs of the phase gadgets just passing through each other. Another set of properties of the phase gadget is that you can decompose them, deconstruct them. So here we have a three-legged phase gadget, and you can remove one of the legs by essentially taking out two CNOTs on the left and on the right. And you can repeat this on the second and third legs, or the third legs, and get these one-legged phase gadgets, which are actually just rotation gates. For those who are familiar with ZX calculus, here this is the density Y and the rotation gates fuse with the spider. These two rules allow us to decompose phase gadgets in arbitrary ways. Here's one way to decompose a three-legged phase gadget, and here are two equivalent ways of writing a four-legged phase gadget. The good thing about phase gadgets is they are architecture agnostic. So for those designing parametrized quantum circuits, you can design the circuit using just phase gadgets without thinking about your architecture, your connectivity. And then once you're done, then you can apply the algorithm, which then synthesize it the best way possible, depending on the architecture. Now we're working with an even more smaller set of rules. Here essentially the 4 rules you need to know for working with phase gadgets in this talk. Essentially, the way to remember these rules is when you have a phase gadget passing through a CNOT, when the colors of the spiders are the same, then the legs don't change. If you have, on the other hand, if the colors of the spiders are complementary, one's green and one's red, then when you pass the phase gadget through the CNOT, then the leg of the phase gadget would appear on the other wire of the CNOT. And this is the same for both green phase gadgets and red phase gadgets. Using these 4 rules, we can then effectively drag the CNOTs and phase gadgets around left and right however you wish. Here's an example for phase polynomials, which are effectively circuits constructed using only Z rotations and CNOTs. And what you could do here is drag the rotations to the right as follows. It doesn't matter the legs exactly, but here you have this normal form, which is essentially a block of CNOT circuits on the left, and then a bunch of phase gadgets on the right, which rotate your input based on the parity. And in fact, this form corresponds exactly to the sum over pass form introduced by Matthew Amy in his phase polynomial paper. And as you notice, which is quite nice. And as you can notice, there's a lot of redundant parameters here. You see the alpha, beta, and gamma 1 circuits fused with the delta 1. So that you only need one of them. And there are other redundancies as well as you drag them across. But this normal form, this method of obtaining normal form also works for circuits with X rotations as well. You can still drag them to the right. They don't commute as well. It's not as clear how they commute, but they do commute sometimes. And we can now focus on the types of circuits on the right and discard the CNOTs and focus on how to synthesize circuits using red and green phase gadgets, using as few CNOTs as possible. So here we arrive at a problem. So given a circuit with interleaving layers of green and red phase gadgets, how do you synthesize it with as few CNOTs as possible? Well, one way to look at it is to, well, you can add pairs of CNOTs anywhere in the circuit because CNOTs cancel out with each other. And then you can drag the CNOT across, which reduces the number of legs in the phase gadget. Here's one example. As you can see, the phase gadgets here have less legs, and less legs effectively mean less resources required to synthesize them, less CNOTs. And in this talk, we're going to look at a way to abstract the simplification method into using just binary vectors and matrices. So to start off with, we're going to take these phase gadgets and then record the positions where the legs appear. So here we have a phase gadget A, Z phase gadget. So we record a Z here, and we add the 1s on the first 2 wires, and then add a 0 here. And we do the same for all the gadgets, and with the phase and the basis labeled. And this allows us to write these column vectors into 2 separate matrices, one for the Z phase gadgets and one for the X phase gadgets. Okay, so then we can start working out how to simplify. So here in the middle, we have the phase gadgets, which are the same as the ones, same as the binary matrices from the previous slide. And now we're going to apply these binary matrices, which are effectively the actions of the CNOT on these phase gadgets. And they are different for the Z phase gadgets and the X phase gadgets, which is why I'm writing them separately. And when you multiply them together in GF2, which effectively is just normal matrix multiplication with remainder 2, we can recombine these matrices to one large matrix above. And as you can see, the 1 entries correspond to the simplified circuit here. Okay, now here's the key lemma for the simplification method. It turns out the CNOTs, the action of the CNOTs on the Z phase gadgets and on the X phase gadgets are related through its inverse transpose. So here we have the canonical example where we just have CNOT. And the way to see this is if you have a Z phase gadget here passing through on the top, then you have 1, 0, and when it comes out, it's unaffected. But here, if you have a Z rotation passing through, then you get a 2-legged phase gadget. And that is precisely what is described by this binary matrix. On the other hand, if you had a red rotation, a X rotation, if you may, the opposite happens. You get the transpose here. And the reason I annotated X and Z here may seem a bit confusing, but this is actually how the CNOT behaves in a Z basis and the X basis exactly. So those kind of mirrored, if you see what I mean. But now let's look at a more complicated circuit. So here's a CNOT circuit with multiple CNOTs, and this is the action on the Z phase gadgets. And if you take this binary matrix, you took the inverse transpose, you would obtain the action on the X basis, which is the binary matrix here on the right. And if you look hard enough, you can see that this is correct. And the proof is relatively simple. You kind of do it based on the CNOTs. So now, given all of this, we are now ready to tackle the problem in its abstract version, which is given the binary matrices which denote the legs of the phase gadget, how do you find the matrix, invertible matrix C, which reduces the number 1 entries in these two matrices as much as possible? So if you look at this example, so these are the original legs. We find a C such that C and C inverse transpose reduces the number 1 entries in these two matrices as much as possible, because the 1 entries correspond to legs, and the fewer legs we have, the fewer CNOTs we need to synthesize the circuit. And what's better is this method, when we push these CNOTs through, when it reduces the number of legs, you can actually repeat the layers of these phase gadgets, and you wouldn't need to repeat the CNOT blocks. You would only need it once on the left and once on the right, because they cancel out. Another way to think about it is you could drag these CNOTs furthermore to the right, and you don't need to write them again. Okay, back to the problem. So this problem is pretty general. You can tackle it using any method you want. We chose to use similar annealing because it yielded pretty good results. And here's an example using Pyzx. And so we use Pyzx to generate and draw these circuits and verify that the circuit is the same before and after simplification, but we didn't use any routines in Pyzx to simplify the circuit. So here we have a circuit made of CNOTs and X and Z rotations, and they you can tell they are actually phase gadgets. So here you have this kind of ladder approach. Here, if you squint it, you can tell that these are the circuits we're interested in. And this is the original circuit with 64 gates. And after we apply our simplification routine, we now get this kind of, first we get a block of CNOTs here, and then a block of CNOTs here, and then a bunch of phase gadgets here with reduced number of legs. And so we've saved about 10 gates here. We can get much better, but I've chosen an example that kind of fits on the screen. Yeah, and so as I mentioned, you can do this for repeating number circuits because these blocks of CNOTs cancel each other as you repeat the number circuits. So there's no need to repeat them. So you get a lot of savings. You get an initial cost of adding these CNOT blocks, but then you get the saving as you repeat the number layers. So when we evaluate this on random circuits by generating random phase gadgets with random basis and random number of legs, these are results we get. As you can see, in the best case, when we have a high number of layers and a few number of gadgets per layer, our simulated annealing routine was able to find a change of basis that reduces the number of legs drastically, and there's no need to repeat the CNOTs. So you get a saving of up to 60%. So conclusions. In this talk, we talked about a simplification method that is, by general, we take these phase gadgets, we combine them, we convert them into binary matrices, and then we use simulated annealing to reduce the number of 1 entries, to reduce the CNOT on depth up to 60%. We use simulated annealing, but You can use other methods. You can use genetic algorithms, for example. One of the kind of drawbacks of this method is the performance. So in our key lemma, we had to take the inverse transpose to obtain the action on the X phase gadget. As you may know, inversing matrix is quite expensive, and there's no built-in method in NumPy to invert these matrices in GF2, so we had to use Gaussian elimination directly, which was quite slow. I think there's probably better ways of doing this, more optimized ways of doing this. We can also change the neighbor selection algorithm, so we select our neighbors in such a way that we can build the inverse transpose incrementally without having to take the inverse every time. And there's probably ways of using this kind of abstraction framework to simplify the circuits further. In this talk, we only discussed the times when we push the CNOTs all the way to the right, but not partially through, like in other papers by Ross and Adrienne. If we push it through, we can probably get better results. Future directions for this, we could think about architecture-specific synthesis. What we've done so far is pretty architecture agnostic, so we don't consider the connectivity of the network. But we could potentially do that by using standard Gauss for synthesizing the CNOT and thinking about other ways of synthesizing the binary matrix afterwards. And then we can also include the cost of the CNOTs into the cost function when we synthesize. If we know the number of layers, we repeat the circuit. Yeah, I hope you enjoyed this talk. Thank you very much.
Thank you very much, Richie. That was a very efficiently delivered talk. And while we're waiting for people to post some questions, I wanted to just ask a clarification, which is when you're doing your benchmarks, where the circuits you were generating were random compositions of Z and X gadgets, or all kinds of poly gadgets, or just random circuits?
Yeah, so this is pretty it's a pretty like artificial kind of data set. So because this is a fragment of something I was working on in my master's thesis. So we were just interested to see how far we could push this. So what we did was we effectively just chose phase gadgets at random. We chose the basis, like the probability half, and then we chose the position of the legs uniformly random. So we just chose a random binary vector for each leg, if that makes sense. It's pretty artificial in terms of the circuit, but I think it seemed to yield pretty good results from my experimentation.
So did you actually have results for more general classes of circuits?
Well, yeah, we didn't kind of apply we didn't generalize the algorithm too much. We weren't looking for like these particular patterns within the circuit. We just focused on generating this fragment of this type of circuits and then apply simplification. But I'm sure we can kind of apply this to a wider class of circuits that contain these gadgets.
I guess the other obvious question I should ask is this kind of ZX alternating structure something that you find in natural examples, or you're going to have to transform your circuit into this shape?
So this appeared, these types of circuits appear quite often in a project. I was looking at quantum machine learning ansätze, and it turns out a whole bunch of kind of gates we're interested in can be just written as phase gadgets plus rotation, which are also phase gadgets of alternating basis. So I also showed that these phase gadgets form a universal set, so you can build a whole bunch of circuits, using just these phase gadgets. So I think you can probably rewrite a whole class of circuits into these.
And we have a question from Lingling Lao, who asks, how can we adapt this to other 2-qubit native gates like the fsim or the xy gate?
Sorry?
Can this method be adapted to different native gate sets than CNOT, in particular things like fsim or the xy gate?
Well, that's a good question. I'm sure it can, but I haven't looked too much into it. Like the conversion definitely exists, but whether it will yield good results is a different question. So I'm not sure about that.
Okay, well, I don't see any more questions in the Slack channel, and I don't see any evidence of anyone typing. So we can just wrap up just now, and we can continue the discussion in Slack.
Sure.
So thank you very much, Richie.